Whenever I lay out the reasons why human beings cannot colonize space, why we are bound to this planet by the chains of biology, the laws of physics, and the realities of economics, why settling Mars is a pipe dream, interstellar travel a fantasy, and a vast majority of our solar system forever off limits to creatures of flesh and blood, a certain retort invariably comes my way. People insist, well, if humans can't manage it, then robots will take our place. Artificial intelligence will be developed, they argue, that has no need for life support, is immune to radiation, and scoffs at the requirement for gravity. Machines capable of replicating themselves will be unleashed, spreading first through the solar system and then across the galaxy, autonomously constructing habitats, extracting resources, and conducting exploration, utterly unburdened by the biological frailties that hold humanity back. Our emissaries to the cosmos will be these robots, our stand-ins among the stars, the legacy of our species, even if we, ourselves, never leave home. This vision of a robotic conquest of space surfaces with great frequency in conversations concerning humanity's cosmic destiny. It is put forward as the definitive answer to every obstacle I've detailed, a method to secure cosmic expansion while sidestepping the insurmountable difficulties of sustaining fragile biological life across immense distances within lethally hostile environments. A kernel of truth exists within this proposition. In numerous respects, robots are, without question, better equipped for space than humans. The vacuum of space, intense radiation, and temperature extremes they can withstand. No oxygen, no food, no water do they require. For years, even decades, without any maintenance, they can potentially continue to operate. Our track record proves this. Robotic probes have been dispatched successfully throughout our solar system, achieving extraordinary scientific feats. Rovers traverse Mars, orbiters circle Jupiter and Saturn, landers touch down on asteroids and comets. The Voyager craft now drift into interstellar space. In the realm of space, robots are effective. For the tasks of exploration and observation, they represent a mature, proven technology. What I intend to explain, however, is why this compelling vision of robotic space colonization is itself fatally flawed and ultimately unachievable. Machines are destined to fail. Not that they might fail, nor that they face formidable challenges requiring solutions, but that they will inevitably fail. This inevitability stems from foundational limitations inherent to robotics, artificial intelligence, autonomous systems, self-replication, and long-term reliability. These limitations render a sustained, independent robotic presence in space an impossibility without perpetual human support from Earth. Robots can certainly embark on brief missions to space with specific, narrow objectives. But space they cannot colonize, a permanent, self-sustaining presence they cannot establish, complex infrastructure over spans of decades and centuries they cannot build and maintain. Themselves indefinitely they cannot repair, to wholly unforeseen challenges they cannot adapt. Human presence in any substantive sense of the word colonization, they cannot genuinely replace. The obstacles blocking robotic colonization differ from those blocking human colonization, yet they are every bit as fundamental and impossible to overcome. Their roots delve deep into the very nature of machines, computation, complexity, entropy, and the inherent boundaries of autonomy and intelligence. Grasping these barriers is crucial, for the fantasy of robotic colonization proves just as misleading as the fantasy of human colonization. False expectations regarding what is possible it fosters, and attention away from realistic, valuable space activities it draws. Let me now clarify precisely what I mean by the phrase colonize space with robots. For varying tiers of robotic activity in space exist, and not all are unattainable. For defined missions, scientific inquiry, the deployment and upkeep of satellites, and assisting with construction on the International Space Station, we already utilize robots extensively in space. All these applications hold value and will persist. The grander conception of robotic colonization is what I contend is impossible. the scenario where autonomous machines establish a permanent, self-sustaining foothold in space, where they erect infrastructure and habitats, where they mine and process raw materials, where they manufacture new robots and components, and where they perpetually repair and maintain themselves, all absent continuous human supervision and logistical support from Earth. This ambitious vision demands several capabilities that contemporary robots do not possess, and that range from extremely difficult to fundamentally impossible to realize. True autonomy, where robots can navigate complex decisions and adapt to unanticipated situations without human input. Self-replication, where robots can construct copies of themselves using only raw materials. Indefinite self-repair, where robots can diagnose and rectify failures and systemic degradation without external assistance. Long-term reliability, where systems can function for decades or centuries without suffering catastrophic failure. And artificial general intelligence, AGI, approaching or surpassing the broad cognitive abilities of a human being. Each of these demanding prerequisites presents profound challenges, and these challenges compound one another, collectively making the notion of robotic colonization impossible. I will begin with the autonomy problem, as it constitutes the most immediate and apparent barrier. Present-day robots function with strictly bounded autonomy. They can carry out pre-programmed sequences, react to particular sensor inputs with predefined behaviors, and execute pattern recognition and elementary decision-making within tightly constrained domains. What they cannot do is manage authentically novel situations, render complex judgment calls, or flexibly adapt to shifting circumstances in a manner a human can. Every single robotic mission in space depends heavily on extensive human oversight and intervention. Teams of mission controllers on Earth monitor streams of telemetry, diagnose emerging problems, upload new command sequences, and modify procedures when events deviate from the plan. This model functions adequately for missions in low Earth orbit or to the Moon, where communication delays measure mere seconds, allowing for near real-time control and troubleshooting. It operates acceptably for missions to Mars, where communication delays range from 4 to 24 minutes, depending on planetary alignment. Direct, real-time control of rovers is impossible, but daily activities can be meticulously planned, and responses to problems can be formulated within hours. The rovers possess some autonomous capabilities, such as basic hazard avoidance, but for primary navigation and scientific target selection, they rely entirely on human planning. This entire paradigm, however, disintegrates for missions that are more distant or of significantly longer duration. At Jupiter, the communication delay is 35 to 52 minutes each way. At Saturn, it is 67 to 84 minutes. At Neptune, the delay exceeds 4 hours each way. For missions beyond our solar system, delays stretch to years. Across such vast distances, meaningful real-time support cannot be provided. To function, robots would have to be truly, fully autonomous. They would need to make all operational decisions, diagnose and respond to system failures, and adapt to unexpected environmental conditions, completely without human aid. Current artificial intelligence and robotics are simply incapable of performing these tasks reliably over extended periods. The core issue is that space environments are intrinsically complex and unpredictable in ways that are exceedingly difficult to anticipate and program for. Spacecraft will inevitably encounter equipment failures, software glitches, sensor degradation, and unexpected environmental conditions, such as dust storms, radiation bursts, or micrometeoroid impacts, that represent novel situations never contemplated during the mission's design phase. Human beings are exceptionally adept at diagnosing such problems and improvising solutions, drawing upon general intelligence, intuition, and creative problem-solving. We can comprehend systems at a fundamental level, reason by analogy, attempt unconventional approaches when standard procedures fail, and communicate and collaborate to untangle complex issues. Machines cannot do any of this with competency even remotely approaching the human level. Machine learning and AI have achieved stunning progress within narrow, specialized domains like image recognition, game playing, or natural language processing. These are, however, highly specialized capabilities trained on massive, domain-specific datasets. They do not generalize to novel situations. When confronted with conditions that fall outside their specific training distribution, they tend to fail catastrophically. They lack the flexible, general-purpose intelligence that humans apply effortlessly to problem solving. Critically, training AI systems for the unique demands of space operations is extraordinarily difficult because space environments and potential failure modes are incredibly diverse and statistically rare. One cannot possibly generate the millions of illustrative examples required to train a robust machine learning system for every conceivable space scenario. Consequently, the autonomy barrier ensures that robots operating far from Earth, or for protracted durations without the possibility of resupply or maintenance from Earth, will inevitably face situations they are unequipped to handle. Systems will fail in unexpected manners. Environmental conditions will diverge from predictions. And in the absence of human intervention to diagnose and rectify these problems, the robots will cease to function and the mission will terminate. This is not a transient limitation awaiting more sophisticated AI. It is a foundational challenge arising from the inherent complexity of real-world systems and the fundamental unpredictability of operating in novel, poorly understood environments. Achieving genuine human-level autonomy would necessitate artificial general intelligence, AGI, a goal that, despite decades of intensive research and investment, remains elusive. Its creation might be impossible, or at a minimum, vastly more difficult than the most optimistic projections in AI suggest. We have, after all, been predicting human-level AI is 20 years away for the past 60 years, with the goalpost continually receding as new layers of complexity are uncovered. Even if we were to achieve AGI, deploying it within space systems introduces a fresh set of formidable challenges. An AGI would demand substantial computing resources, consuming significant energy and adding considerable mass to a spacecraft. Radiation in space is relentlessly damaging to electronics, including the processors and memory that would host such an AGI. Shielding these systems from radiation necessitates heavy protective layers, further increasing mass. The entire computing infrastructure would require dedicated cooling and power systems, becoming a major subsystem that itself would require maintenance and be prone to failure. Furthermore, any AGI deployed for such a critical purpose would need to be supremely reliable and exhaustively tested, as it would be making vital decisions autonomously, with no human in the loop. Yet testing an AI for all possible scenarios is a logical impossibility. The space of potential situations is infinite. One cannot prove with certainty that an AGI system will correctly handle every unforeseen circumstance. This means entrusting potentially civilization-scale resources to a system that may harbor subtle bugs or failure modes manifesting only under rare, untested conditions, creating an enormous and potentially unacceptable risk. There is also the profound and unsolved alignment problem, ensuring that an AI system's goals remain perfectly aligned with human values and intentions, and that it does not pursue instrumental sub-goals that conflict with our interests. An AI tasked with interstellar construction might, for instance, optimize for maximal resource consumption and replication without any regard for preserving scientific data, preparing infrastructure for eventual human use, or adhering to ethical constraints we would impose. Ensuring AI alignment over the vast timescales and through the potential self-modification involved in a colonization project is a problem that may be fundamentally unsolved and perhaps unsolvable. Thus, the AI prerequisites for robotic colonization are not merely extreme. They may be impossible to satisfy. We require an artificial general intelligence that does not currently exist and may never exist. We require that this intelligence be reliable, safe, and aligned, all currently unsolved research problems. We require it to operate in the harsh, resource-constrained environment of space. And we require this entire suite of capabilities to function autonomously for decades or centuries, a feat we have never demonstrated, even for vastly simpler systems. The AI barrier alone likely suffices to render robotic space colonization impossible, independent of all other technical hurdles. Now, let me delve into the reliability problem, which compounds the autonomy challenge exponentially. All machines, without exception, degrade and ultimately fail over time. Wear fatigue, corrosion, radiation damage, and other inexorable physical processes see to this. Entropy is an unyielding universal law. Systems do not maintain themselves. They demand continuous maintenance and, eventually, complete replacement. On Earth, we acknowledge this reality and construct immense maintenance infrastructures. We service machinery regularly, replace worn components, and rebuild or retire systems when they degrade beyond repair. We maintain global supply chains for spare parts, employ armies of skilled technicians, and operate factories capable of manufacturing replacements. In space, none of this supporting infrastructure exists. Robots intended for long-term presence must therefore operate for extended periods with zero maintenance, or with only whatever self-maintenance they can perform, a prospect that is extraordinarily difficult. Consider the longest operating space missions as benchmarks. The Voyager spacecraft, launched in 1977, continued to function and return data over 47 years later, a testament to remarkable engineering longevity, far surpassing their original design specifications. They achieved this through meticulous design employing robust, redundant systems, conservative operational choices to minimize stress, and the fact that their mission profile is fundamentally simple. They are essentially coasting on ballistic trajectories, transmitting a steady signal, not performing complex, interactive tasks. Most spacecraft fail much sooner. The Mars rovers Spirit and Opportunity operated for 6 and 15 years, respectively, before succumbing. Curiosity has operated for over 12 years, but shows signs of steady degradation. It is crucial to note that these rovers were designed for 90-day missions and spectacularly exceeded expectations, yet they remain ultimately limited by accumulating irreparable failures. Opportunity's end came when a global dust storm blocked its solar panels. Spirit became trapped in sand. The Hubble Space Telescope has operated for over 3 decades, but only because of multiple servicing missions by space shuttle astronauts who replaced failed gyroscopes, instruments, and upgraded systems. Without those human repair missions, Hubble would have been defunct decades ago. The empirical evidence is clear. Even with our best engineering, space systems fail on timescales of years to decades. Failures are often catastrophic, ending the mission entirely rather than causing a graceful degradation of capability. For a vision of robotic colonization that requires uninterrupted operations over decades, centuries, or even indefinitely, these reliability limitations are fatal. Systems will fail long before anything resembling a self-sustaining presence could be established. Without an inherent capacity for comprehensive repair, they simply become very expensive orbital or planetary debris. The space radiation environment presents a particularly destructive challenge for long-term reliability. Cosmic rays and solar particle events cause single-event upsets, where energetic particles strike memory or logic circuits, flipping bits and causing computational errors or crashes. Over time, cumulative radiation damage in semiconductors degrades performance and eventually causes permanent failure. Space-grade electronics must be radiation-hardened, using specialized materials and designs, but this process is expensive, resulting in components that lag far behind commercial counterparts of performance. And even rad-hard systems have finite lifespans under sustained exposure. Beyond the protective bubble of Earth's magnetosphere, radiation exposure is severe and unceasing. On the Martian surface, the annual radiation dose is roughly 200 to 300 millisieverts. In interplanetary space or near giant planets like Jupiter, it is far higher. Physics itself imposes hard limits on the operational lifetime of electronics in these environments. You cannot engineer components that last indefinitely under such bombardment. Mechanical systems are not spared. In the vacuum of space, moving parts can still wear due to atomic-scale interactions. Lubricants can evaporate or polymerize under radiation and extreme temperature cycling. Bearings, gears, and actuators have finite cycle lives before they fail. Seals can develop leaks. Materials fatigue under constant thermal stress. The wheels on the Mars Curiosity rover, for example, are accumulating holes and tears from driving over sharp rocks. Damage that is irreversible and will ultimately limit its mobility. You cannot replace a rover's wheels without a repair capability far beyond what any current robotic system possesses. The reliability problem therefore dictates that all robotic systems have an inherent, finite operational lifetime, after which failure becomes inevitable. These lifetimes are measured in years to, optimistically, a few decades, not centuries, and certainly not on indefinite timescales. This fundamental limit makes long-term robotic colonization impossible without one of two untenable solutions. Either a continuous stream of replacement robots launched from Earth, which contradicts the very idea of self-sustaining colonization, or the achievement of perfect self-repair capabilities, a challenge of staggering difficulty, which I will address next. This brings us to the self-repair challenge, often proposed as the panacea for reliability issues. The concept is elegant. Robots would be designed to diagnose their own failures, fabricate or retrieve replacement parts, and execute repair procedures, all without human intervention, thereby restoring functionality and achieving indefinite operational life. In practice, self-repair is orders of magnitude more difficult than this simple description implies. It requires an integrated suite of capabilities, each formidable on its own. Fault detection and diagnosis. Identifying what is broken and why. Repair strategy decision-making. Determining the appropriate fix. Physical manipulation. Accessing the failed component and installing its replacement. Part fabrication/inventory. Having the correct replacement part available, either from a carried inventory or manufactured on-site. Verification. Confirming the repair was successful. Each step poses monumental problems for an autonomous system in space. Fault diagnosis is notoriously tricky. Many failures are subtle or intermittent, and a failure in a sensor itself can corrupt the diagnostic process. Physical manipulation for repair requires a dexterity, adaptability, and problem-solving ability that far exceeds current robotics, which excel at precise, repetitive tasks in controlled environments, not improvisational jury-rigging in confined, variable spaces. The part availability problem is perhaps most crippling. A robot could carry a vast inventory of spare parts for every conceivable failure, but this adds prohibitive mass and complexity. The alternative, fabricating parts on demand, requires carrying advanced manufacturing equipment like 3D printers and raw materials. While 3D printing has advanced, it cannot currently produce the most critical components that are likely to fail. Advanced electronics, CPUs, sensors, high-efficiency motors, or specialized optics. The dream of in-situ resource utilization, mining asteroids for raw materials, to feed this manufacturing adds another entire layer of staggering complexity, requiring its own suite of equipment that itself must be maintained. Thus, self-repair confronts a vicious paradox or catch-22. A system simple enough to be comprehensively self-reparable would lack the sophistication needed to perform meaningful colonization tasks. Conversely, a system complex enough to perform colonization would have such intricate dependencies and specialized components that comprehensive self-repair becomes a practical impossibility. You end up needing repair systems nearly as complex as the original system, and then you need systems to repair those repair systems, leading to an infinite regress of complexity. Software and cybersecurity introduce another dimension of fragility. Modern spacecraft rely on millions of lines of software code. Bugs, bit flips from radiation, and security vulnerabilities can cause failures that are often harder to diagnose and fix than hardware issues. Debugging software remotely or autonomously is a profound challenge. Software also requires updates and patches to fix vulnerabilities, a process that itself can introduce new failures if done autonomously without human oversight. An autonomous colony would need AGI not just to fix hardware, but to comprehend, debug, and modify its own software, a requirement bordering on the metaphysical. The pinnacle of the robotic colonization fantasy is self-replication. The idea that a single robot could land on an asteroid or moon, mine raw materials, and construct a perfect copy of itself, initiating exponential growth. This concept, inspired by biological reproduction and formalized by John von Neumann, is the engine behind visions like von Neumann probes spreading through the galaxy. The obstacles here are not merely engineering hurdles, but approach fundamental limits. First is the complexity barrier. A machine capable of building a perfect copy of itself from raw materials must contain, within itself, the entirety of the industrial capacity needed to manufacture every single one of its own components. This includes microprocessors, sensors, actuators, structural members, wiring, and, most challengingly, the manufacturing tools themselves. The minimum complexity for such a universal constructor is astronomically high, likely equivalent to cramming an entire modern semiconductor fab, metallurgy plant, and precision machine shop into one package. This is a feat with no precedent or clear path to realization. Second is the closure problem. A self-replicator must achieve near-perfect closure, meaning it can produce all necessary materials from locally available resources without any external inputs besides energy. Our technology uses elements from across the periodic table. The smartphone in your pocket contains dozens of different elements, each requiring specific, energy-intensive processes to extract and refine. It is fantastically unlikely that any single asteroid or planetary body would contain all necessary elements in accessible concentrations, and the energy required to process them would be enormous. Third are timescale and energy issues. Even if possible, the replication cycle would be extraordinarily slow, likely taking years or decades to mine, refine, and assemble a single copy. This sluggish pace negates the concept of rapid exponential growth. The energy required for this industrial activity would be massive, demanding vast solar arrays or nuclear reactors that themselves must be built and maintained. Finally, there is the evolution problem. With imperfect replication, a near certainty, mutations in design or software would occur. Natural selection would then act on the population of machines, potentially favoring selfish replicators that cut corners on quality or parasitize others to replicate faster, leading to a breakdown of the intended function, a robotic tragedy of commons. Preventing this requires either perfect replication fidelity, impossible, or built-in selection mechanisms, adding yet more layers of untenable complexity. When we examine specific proposals like von Neumann probes for interstellar exploration or asteroid mining colonies, we see these fundamental barriers play out. A von Neumann probe would need to survive a millennia-long journey, then upon arrival at an unknown star system, autonomously locate resources, build its industrial base, and replicate, all with AGI-level intelligence and perfect reliability. The timescales involved, thousands to millions of years, dwarf any plausible system lifetime, and the data it might send back would reach an Earth that may no longer harbor a recognizable civilization. Asteroid mining, while closer to home, stumbles on the economic bootstrapping problem. The infrastructure required to mine and process asteroidal materials is so vast and expensive that it could only be justified if there were already a large, thriving space-based economy to purchase those materials. But such an economy cannot exist without the affordable materials first. This circular dependency, combined with the immense technical challenges of autonomous operation in microgravity, makes the business case perpetually recede into the future. It may always be cheaper to launch materials from Earth than to build the autonomous space industries needed to get them from asteroids. In light of these cascading limitations, autonomy, reliability, self-repair, self-replication, and economics, the grand vision of robotic space colonization collapses. It is not a viable backup plan for human failure. Robots are superb tools for exploration, observation, and executing specific, time-limited missions with Earth-based support. We should continue and enhance these efforts, building better orbiters, rovers, and telescopes to understand our universe. But we must relinquish the seductive fantasy that machines can independently build a lasting, growing, self-sustaining human legacy among the stars. The barriers are not merely technical. They are logical, physical, and economic constraints woven into the fabric of reality. This conclusion, that neither biology nor machinery can grant us a cosmic empire, carries profound philosophical weight. It dismantles a central narrative of modern technological optimism, that progress is unbounded and that humanity's destiny is to fill the galaxy. This narrative has provided a sense of purpose and a next frontier for generations. Accepting its falsehood can feel like a profound defeat, a concession to cosmic claustrophobia. Yet, this realization is not a cause for despair, but rather a clarion call for a profound shift in perspective. It grounds us literally and philosophically on Earth. If we have no planet B, then planet A becomes infinitely more precious. The imperative shifts from escape to stewardship, from dreaming of other worlds to preserving and perfecting this one. Our cosmic significance is not derived from how many stars we claim, but from the quality of consciousness, knowledge, and civilization we cultivate right here. The universe may be forever closed to physical colonization, but remains wide open to our wonder, our science, and our understanding. Our telescopes can still map its farthest reaches. Our probes can still whisper back data from its corners, and our minds can still comprehend its laws. That is a legacy worthy of a truly intelligent species. Our destiny is not to conquer the cosmos, but to comprehend it, and in doing so, to cherish and sustain the rare, beautiful, and fragile world that made that comprehension possible.